this new video. Today, we will be presenting a scientific article that explores the application of quantum computing to an optimization problem, the aircraft loading. This article was written by teams from IonQ and Airbus. First, we will begin with an introduction to the content of the paper. Next, in the background section, we will describe the context of the problem as an optimization problem. Third, we will explain how the problem is formulated for quantum computing and how the constraints are assignated. Fourth, I will present the result from the paper, followed by the conclusion. And finally, I will share our personal opinion on the work. In this paper, the author addressed an aircraft loading optimization problem. To tackle it, they proposed a variant of the QROR algorithm called the multi-angle layered variational quantum algorithm, or MAL-VQA. They also introduced a new formulation of cost function designed to better handle inequality constraints. Let's talk a bit more about the aircraft loading problem. This problem consists in maximizing the load of an aircraft while respecting several constraints, such as the total capacity of the plane, the position of the center of gravity, and other physical or operational limits. We will dive deeper into those constraints later. In essence, the aircraft loading problem is an constraint combinational optimization problem. It actually appears as a variant of the well-known knapsack problem. As a result, it is also classified as an NP-hard problem, which is exactly why it is interesting to try and tackle it using quantum computing. Definition of the problem. We have M containers to load. For simplicity and uniformity, each container can belong to one of three types based of its dimension. On this aircraft, there are n available positions as shown in the illustration. Depending on the container type, a position can either hold one or two containers, or in some cases, a container may require two positions. To evaluate our objective, which is to maximize the total load, we define a cost function denoted H. H represents the total weight of containers loaded onto the aircraft. It is a function of x, where x is the set of m containers, each assigned to specific position among the n available ones. So we are looking for the set x0 that maximizes the function h over all possible configurations of x. To set x, the set x can also be seen as a bipartite graph between the m containers and the n positions in the aircraft. From that, we can define a binary matrix of size m times n, where each element describes whether a container is placed in a given position. If we denote x, e.g., as the matrix element that equal 1 when container I is loaded at the position G, and WE as the weight of container I, then the objective function H corresponds to the total weight of all the containers loaded onto the aircraft. But it is important to note that this objective alone does not take the constraints into account. So to complete Hamiltonians, the one used in the Kubo formulation is actually the sum of this objective Hamiltonian and the constraint Hamiltonians, each weighted by their respective penalty coefficients. Now, the problem is mathematically and classically well defined, but to make it suitable for quantum computing, it needs to reformulate or more precisely mapped into a form that quantum algorithm can handle. For binary combinatorial optimization problem, the common approach is to replace the binary variable 0, 1 with 1 minus 1, which correspond to the eigenvalues of the Pauli Z matrix. This transformation is essential because quantum systems naturally work with qubit states that relate to those eigenvalues. So for a given problem involving m containers and n positions, this mapping strategy requires us to use m times n qubit. Now let's see how the quantum secret is made. To build the Hansat, the author used a multi-angle layered variational quantum algorithm, or MALVVQR. In this approach, each layer consists of two parts. First, a set of parameterized LU rotation is applied to each qubit. Then a second parameterized circuit is applied specifically designed to create entanglement between the qubits. This two-block structure can be repeated multiple times to increase the expressiveness of the ansatz. What distinguishes this ansatz from the traditional QRO ansatz is that each rotation U get as its Hall parameter. In contrast, conventional QRO typically use only two parameters per layer, one for the mixed Hamiltonian and one for the closed Hamiltonian. The author justifies their choice by explaining that assigning a separate parameters to each gate allows them to reduce the circuit depth while maintaining the expressiveness of the ansatz. Talk about the constraint. In this paper, the author proposed to treat the constraints like penalty, instead to include it in the Hamiltonian via slack variable as is often made in QRO. In this way, we avoid an too much qubit as slack variable required often a lot of qubit. So the constraints that a set X have to satisfy to be a valid solution are first the total mass of the load containers may not exceed the payload capacity of the aircraft, W max. This constraint is pretty intuitive. Another intuitive constraint is that the load should not depress too much the center of gravity of the plane. Mm. Let's now continue with the constraints. A valid solution must also satisfy the maximum shear constraint. These constraints relate to the aircraft's structural capacity to support the load locally. Indeed, even if the overall load distribution respects the center of gravity limit, the aircraft can still be damaged if a particular section of the fuselage is subjected to excessive shear force. These constraints ensure that no part of the aircraft structure is overstressed by the accumulation of mass near or beyond a given point. Next comes the slot assignment constraint. It is obvious that a container placed in one position cannot be placed in another. These constraints ensure that um, We continue with a constraint. The previous constraints do not apply exactly to type 3 container because placing one of them requires two consecutive slots. However, just like with type 1 and type 2 container, once a container is assigned to a position or a pair of positions, it cannot be assigned elsewhere. This constraint is introduced to capture that specific requirement. In addition to making sure that the same container is not placed in multiple positions, we also need to guarantee that each container fits within the capacity of the slot it is assigned to. More specifically, Type 1 and Type 3 container fully occupy a slot, while a Type 2 container only take up half of it. This constraint enforces that logic. And finally, this last constraint target a trivial solution, the all-zero state, which the author specifically penalizes it in the cost function. Now let's see a cost function in detail. One of the main contributions of the author lies in the design of the cost function. They propose a nonlinear penalty function that allows for more customized penalizations of solutions that violate constraints. In addition, when computing the expectation value, they introduce the conditional value at risk method. Roughly speaking, instead of taking the average of all sample results, Seva focused on the subset of solutions with the lowest energy values and computes the average over just those. This helps Git to optimize toward the most promising solution. Result, we are working with an instance involving 4 containers and 3 slots, which require 12 qubits. The maximum allowed weight is 14 kilograms. The algorithm was run on ARIA, Yonkers Quantum Processing Unit. On the left, we can see the probability histogram. We observe that the optimal solution is clearly isolated with a significantly high probability compared to other. And on the right, we can see the corresponding arrangement. We're still working with the ARIA QPU, but this time the search for the optimal parameters on the answer is performed on a classical CPU. The author tests two problem instances. For one, they research the optimal solution with this result. The author aims to highlight the high fidelity of the 2-qubit gate on the ARIA quantum processor unit. Now here we get for the first instance of 4 slots and 4 containers. We can clearly see that the optimal solution is well separated from the other output. On the left, we can see the corresponding arrangement again. We have the same result for the second instance of 4 slots and 5 containers. The optimal solution is well isolated for the other output. The author found another instance of the problem, 7 containers and 4 slots with a maximum weight of 23 kilograms. This time they use a different quantum processor unit called FORT, which has a particular feature. Indeed, they first start the optimization on a simulator, stop it before it converges, and then use that result as the starting point for the optimization on the fourth quantum processor unit. Let's see the result. Here, here the optimization result on the fourth QPU. The pink histogram represents inference. The green one is the full quantum processing unit run, and the blue one corresponds to the ideal simulator. Just like on ARIA, the optimal solution stands out clearly. We also notice that inference performs better than the full QPU execution. Of course, the highest probability is observed on the simulator since it does not fully account for noise. Yes, so yes, that is exactly what I was saying about the figure. So you can pass this slide. Let's take a closer look at the instance with 7 container and 4 slots with a maximum weight of 23 kg executed on the fourth QPU. The problem was initially optimized using an internal simulator on fourth. This led to two solutions, one that we presented earlier in the histogram and another that was selected to be executed as an inference experiment on the fourth QPU. And here it is the result shown on the next slide. This is the result. The optimal solution was reached with a probability of 35%. The author also point out that this experiment demonstrates the algorithm's ability to converge to different degenerate solutions. The conclusion of this review. This paper proposed a quantum approach to find the optimal loading of containers in an aircraft. The author started by formulating the problem as a QUBO, then introduced J algorithms called MAL-VQA. They presented how they incorporated the constraints and designed the cost function. They also described how they executed the algorithm on Yonke, quantum computer, ARIA, and Ford. Finally, they suggested direction for scaling up the approach, such as decomposing large instances into smaller subproblems, exploring alternative algorithms like quantum imaginary time evolution, or running on devices with a higher qubit count. Alright, now there are still a few unclear points and some criticisms I'd like to raise about this paper. First, the cost function refers to a degree of violation, but this concept is not clearly defined anywhere in the paper. Second, the relationship between the penalty function, the cost function, and the error function are not clearly explained, which make it hard to fully understand the logic of the information. Another issue is the use of the abbreviation MAL-QUA. It originally came from a paper titled Multi-Angle Quantum Approximate Optimization Algorithm, where the abbreviation matched the title. However, in this paper, the author cite the same source, but refer to it as a multi-angle quantum alternating operator algorithm, which creates confusion and inconsistency in interpretation. Finally, regarding the strategy to initializing the quantum optimization with parameters from a classical optimizer, how do they ensure that the remaining problem is still hard if the classical optimization already bring the system close to the bottom of the cost landscape? In the quantum step still necessary or clearly beneficial? That is all from me. I hope you enjoyed this presentation and I will see you next time for another paper.